So now let's look at part B of the materials topic, which is metals. And I guess there's one theme, if you like, that really comes through this topic is really our electrochemistry topic and the electrolytic cells. So again, we looked at some of the stuff around electrochemistry, probably more at galvanic cells in stage 1 chemistry. So if you need to, that might be worth having a look back at that. But we'll also look at some other things around metals, but probably one of the most key concepts here is some of the work around the electrochemistry and the redox reactions that we've looked at previously. Let's get into it. So I'm going to start this topic by just looking back at what is an electrolytic cell and revising that concept. And if you remember, I actually haven't written this here, but it's sort of implied from the diagram. An electrolytic cell is one where we use electrical energy to drive a non-spontaneous reaction. Probably is worth making a note of that. I'm just going to pause and actually add that to this. Okay, so I've added that definition there. That is an important one to remember. Now, there's a couple of classic electrolytic cells. This is the one where you copper plate something from a copper sulfate solution, one that hopefully you've done in the lab at some point in year 10, 11 or 12 or maybe all 3 years. The other example that we use in the lab of an electrolytic cell was the Hoffman voltammeter, where we used basically an electrical energy supply, a power supply, to basically break up water into hydrogen and oxygen. So that one's not so related to metals, so that's why I've chosen this copper plating type cell. And what we have in that cell is we have 2 electrodes. Often we use graphite or carbon electrodes. The negatively charged electrode, what we will see is we'll see copper metal forming on that electrode, and that happens because the copper ions in the copper sulfate solution, so this is an aqueous copper sulfate solution that contains basically aqueous copper ions and aqueous sulfate ions. We call that an electrolyte. So any solution that contains ions, which can therefore conduct electricity, is called an electrolyte. As the electrons come through the circuit, they combine with the copper ions to form copper metal. This is a gain of electrons, therefore a gain of electrons means it is reduction. Therefore, because it's reduction, we refer to this electrode as being the cathode. So hopefully that's all revision. I haven't put a huge amount of detail there, but hopefully there's enough there to bring back memories for that process. Now, if we've got the gain of electrons at this electrode, we almost must get the loss of electrons at this. And if you remember doing this experiment, you'll all see little bubbles form on this other electrode. Those bubbles are oxygen gas, and that forms as water, basically breaks down into oxygen gas and loses the electrons. Just here you can see I've used the half equation method to balance that. I've just put a reminder here in case you've forgotten about that. You would start by balancing elements other than oxygen and hydrogen. So in this case there is no other, so we can skip that step. You'd balance out oxygen using water. So we had O2 on this side originally, H2O, that was our redox couple. So we need 2 water here, so we've got 2 oxygen both sides. Then we balance out the hydrogens using H+, so we've got 4 hydrogens here, so we added the 4 hydrogens here. And then we balance out the charge using electrons. So we had a 4+ charge here, so we added 4 electrons here to balance that out. That's a loss of electrons, therefore it's oxidation, therefore this electrode is the anode. So hopefully that has given you enough to remember how to identify the anode and cathode and their charges, as well as the direction of ion and electron flow in an electrolytic cell, given sufficient information. I always remember negative cathode, positive anode in an electrolytic cell. I always remember it because the negative electrons, well, the negative electrons are negatively charged and they're pumping the electrons into the copper. So because that's gain of electrons here, that must be the negative. Some people just remember it. There is other ways to remember it, but that's how I like to remember it. In terms of ion flow, I probably should highlight here, so I might just add that to the diagram. What would happen here is negative charge is obviously flowing this way through the circuit, so clockwise. So in the solution, we would get negative ions would go that way, so that would be like the sulfate ions, and the positive ions, like the copper ions, would be going towards the negative electrode. So those positive copper ions are getting attracted to that negative electrode where they gain those electrons. So basically a flow here of negative charge, hang on, I'll use my pointer, a flow here of negative charge in a clockwise direction is basically means that the positive charge would need to flow in the opposite direction because it's oppositely charged. Write electrode half equations for an electrolytic cell given sufficient information. So I've just gone through that again. The sufficient information is usually what is the redox couple. So water is going to oxygen. You'd be told that. Copper ions are forming copper metal. That would be told or implied from the question. Then you would just need to use that balance half equation method to complete the picture. So that is a brief introduction and or recap of electrolytic cells. Let's keep moving. So now we'll get into the metals, which is really what this subtopic is all about. And it's the idea particularly about how we produce metals. So you probably know most metals are mined. When they are mined, they are not in the form of the metal, maybe with the exception of gold, and we'll talk maybe about silver later on, where we do find native gold in the environment, but things like iron is found in iron ore, alumina or aluminium is found as a mineral called bauxite, which contains aluminium oxides or aluminium hydroxides. Zinc is found in a mineral called sphalerite, which contains zinc sulfide. Copper is found in various forms. It might be as a copper sulfide or it might be as a copper carbonate. So generally, most metals are found as in an ionic or their ion form. Or we say that they are combined with other atoms. So they've basically lost their electrons and they're combined with a negatively charged ion of some form. So the production of the metals needs generally for that metal to be converted from the iron back into the metal, which is the reduction process that we just talked about in the electrolytic cell. However, before we can do that, we often need to convert the mineral into a form ready for reduction. So what this dot point says is explain with the aid of equations the methods designed for the conversion of a mineral to a metal given sufficient information. So here, firstly, the given sufficient information. You do not need to remember the details of all these processes. You will be given information and you need to interpret it. These questions will often be combined with questions about like chemical industry and flowcharts that we did earlier in the year. But I just want to talk you through a couple of examples so you know what's the sort of things that they're looking for when they give you sufficient information, if you like. So two common ones that we talk about. Aluminium. I spent 5 years of my life looking at this chemical reaction. Aluminium is mined as a mineral called bauxite, which contains a mixture, well, it contains lots of things, but in general it contains a mixture of aluminium hydroxide in a mineral called gibbsite and iron oxide. Now, before we can basically get ready to reduce it, we need to get all the iron oxide out. So we mix it with sodium hydroxide. The aluminium hydroxide will dissolve. We can see this reaction here. Aluminium hydroxide plus hydroxide forms this ion here, which we call the aluminate ion, plus water. Now the iron oxide won't dissolve in the sodium hydroxide, so that just settles out to the bottom, and then you basically just pump off the liquid part, which contains the dissolved alumina, the aqueous aluminate ion. This aluminate ion solution, or aluminate ion in solution, is then seeded with a small amount of this pure gibbsite, and all of the aluminium oxide crystallises out. So you get basically left with relatively pure aluminium hydroxide or gibbsite. This is then dried in a kiln to produce alumina. So we heat this up, and we get left with aluminium oxide and water. The aluminium oxide is the form that is ready to get sent off to be turned or to be reduced to aluminium metal. So that's just going through how we go from bauxite to aluminium or alumina, aluminium oxide, which is ready for reduction. We'll get to how we reduce these things in the next part of the video. Similar thing with zinc, it's mined as zinc sulfide, which is insoluble. So we can't just dissolve that and say like the the bauxite was designed in sodium hydroxide. So we actually initially roast that in the presence of air, which contains oxygen, and that produces zinc oxide and sulfur dioxide. Now, we talked about this earlier in the chemical industry. This sulfur, and also when we talked about acidic oxides, so non-metal oxides being acidic, this sulfur dioxide can be reacted with oxygen, which then, so sulfur dioxide plus oxygen makes sulfur trioxide. Sulfur trioxide can then be reacted with water to make sulfuric acid. The sulfuric acid actually gets used later in this process. We're about to talk about that. So this is sort of revision of that chemical industry stuff, if you like. The zinc oxide will react with the sulfuric acid to produce aqueous zinc ions. So zinc oxide plus sulfuric acid, we get aqueous zinc sulfate. So these is dissolved. We've got aqueous zinc ions plus water. This is the form that's ready for reduction. We can then go and do an electrolytic reduction, like I talked about in the first part of this video, to produce the zinc metal. We can't do that directly though with the zinc sulfide. We have to go through this conversion process to get it into a form that's ready for reduction. Again, you don't need to remember the whole details, although there is stuff in the course about these reactions of non-metal oxides with acids, but you need to be able to, given sufficient information, again, interpret and understand what that is talking about. So now let's move on to how we reduce that into the metal. So the reduction process depends on the reactivity of the metal. Hopefully you are familiar with this sort of reactivity series for the metal, from things like potassium and sodium that will react violently with water. They are so reactive and want to lose their electrons so much, through to things like gold, which is very, very unreactive. And how we reduce a metal depends on where it lies on these series. So if we look at the top here, from aluminium and above, these are our most reactive metals. These are all more reactive than water. That means that the electrolysis must be done from a molten salt. So a molten salt is where we take, say, potassium chloride or sodium chloride or calcium chloride or aluminium oxide, and we literally melt the salt. So we don't dissolve it in water, we melt the salt. Why do we need to do this? Well, if we dissolve them, if water is present, then the water would be reduced to form hydrogen gas, like we saw in the Hoffman voltometer, rather than to produce the metal. So we can't have any water present. So what would basically happen, I've done a little diagram here. If we were talking about the aluminium example, we would melt the aluminium oxide. We would have our two electrodes in there. At the negative electrode, we would get reduction, so the cathode. The aluminium would gain electrons to form aluminium metal. The oxide ions would lose electrons to form oxygen gas. So that would be how we produce our aluminium metal. Obviously, if water was present, we would get hydrogen formed at this electrode rather than aluminium. The The problem with this process is it requires lots of energy to melt the salt. These have typically melting points of hundreds of degrees, up to thousands of degrees maybe in some cases. So it's a very energy intensive purpose to both melt the salt, then pump the electricity in to reduce it. However, for the reactive metals, that's what we need to do. When we get into this next block, from zinc, iron, nickel, tin, lead, copper, mercury. By the way, this reactivity series will be given to you in an exam, at least all the ones you need to know. It will be on your the back of your periodic table, so you don't need to remember that. What we would see is that we can use either electrolysis of the aqueous solution. So I talked about with copper at the start of this video, how we would do that. So you've already sort of gone through that example. The advantage of this is it requires less energy than the molten salt or the carbon reduction, which I'm about to talk about as well. So often, if we can easily get the mineral into a form where we can do aqueous electrolysis, we would favour that. But that means we need to be able to easily convert it to that form, and it needs to be able to one that will dissolve in an electrolyte so that we can reduce it. And then often with these things, for example, iron, it's not easy to get iron into a form where it is soluble, and we can use this method. So the other method that we use is what's called carbon reduction. This is what happens in a blast furnace at somewhere like Whyalla. You start by taking carbon in the form of coal or coking coal, and you react it with a limited supply of oxygen to form carbon monoxide. That carbon monoxide is then reacted at very high temperatures with the iron oxide, and we produce iron plus carbon dioxide. Again, because this all needs to be done at very, very high temperatures, it requires lots of energy. It also involves the burning of coal, so we get lots of carbon dioxide emissions and the problems associated with global warming and that being a non-renewable resource and all of that sort of thing. So yeah, that is our carbon reduction. So they are our two methods that we would generally use for these metals of, if you like, medium reactivity. At the other end, we have silver and gold. These are our least reactive metals. Particularly gold is found uncombined in nature. So basically gold is so unreactive, over the whole age of the Earth, it hasn't reacted in general to form compounds with other ions. It hasn't been oxidised, if you like. It hasn't lost its electrons in interactions and combined to form salts like all these things or minerals. So that's why we are able to find it uncombined in nature. You do actually occasionally find a little bit of copper uncombined in nature, and that is nearer this end of the spectrum. But yeah, because of that, because it's the least reactive, that's why they're found uncombined. So hopefully we've covered all the key points here, given the position of metals in an activity series of metals. So as I said, given, you'd be given that. Predict whether the metal is likely to occur in nature in a combined or uncombined form. So all of these more reactive ones will be combined because over time they would have been oxidised, lost their electrons, combined with negatively charged ions, except for silver and gold at the bottom. Predict and explain the likely method of reduction of the metal compound, including electrolysis of molten compound. That's the one for our most reactive. Electrolysis of an aqueous solution of the metal compound, and the use of carbon as a reducing agent for these two here. Explain the benefits of one method of reduction compared with another given relevant information. Energy, high temperatures, carbon emissions, all of those things are the benefits of, or the benefits or disadvantages of the various techniques. So, hopefully that gives you an insight into the production of metals. Thank you.